Welcome to AI Podcast. Today we're unpacking a NeurIPS 2025 paper called Decoder Hybrid Decoder Architecture for Efficient Reasoning with Long Generation.
That's a mouthful. Give me the headline first. What's the one thing people should remember?
The headline is simple. The authors found a way to make long chain of thought generations much faster while keeping accuracy about the same. They do it by reusing a compact memory of the prompt instead of rereading the whole thing at every step.
Reusing a compact memory. Okay, I'm intrigued. Who's behind this?
It's a collaboration led by Liliang with folks at Microsoft, and Congcong's son from Stanford is on it too. Big mix of industry and academia.
Got it. So what problem are they solving exactly? We've had long context models for a while now.
Right, but the pain shows up when the model has to generate a lot of tokens. Even if you cache the prompt smartly, the model still keeps reaching back to that cache during decoding. Think of it like writing a long essay and walking back to the library shelves for every single sentence. The walking becomes the bottleneck.
So the time sink isn't understanding the prompt, it's the constant back and forth while speaking the answer.
Exactly. Prefill, the part where you read the prompt, is fine. The drag is the generation phase. Every token wants to peek at the entire memory again.
And previous fixes didn't quite crack that?
Prior work like Yoko reduced how often we recompute attention by caching once and reusing it, which was a big step. And hybrid models with state space layers like Samba scan long sequences quickly. But two things lingered. First, cross-attention layers still do a lot of key-value reading during decoding. Second, state space models alone sometimes struggle when the task is find a very specific needle in the haystack.
So we want the speed of state space models and the precision of attention, without the heavy memory traffic every time we generate a token.
That's the sweet spot. This paper proposes a two-stage decoder that tries to get both.
Walk me through that design slowly. 2 stages.
Stage 1 is what they call the self-decoder. It's a hybrid stack that includes a state space model. Its job is to read the prompt once and distill it into a strong internal memory. Picture an expert note-taker who turns a 100-page dossier into a really good set of index cards.
Okay, so we've got crisp index cards after stage 1. What's stage 2?
Stage 2 is the cross-decoder. Traditionally, it would use cross-attention layers to look back at the prompt representation every time it generates a new token. Here's the twist. They replace a bunch of those cross-attention layers with a tiny module called a gated memory unit.
Gated memory unit, what does it actually do?
Think of it like a mixing valve. At each step, it takes two things: the current layer's activations and the compact memory produced by stage 1. Then it gently gates how much of that memory to blend in. No attention maps, no big matrix of keys and values to fetch. It's just a small gate that says, hey, add a bit of what we already summarized.
So instead of trekking back to the library stacks, you're pulling from the index cards on your desk.
Exactly. And that desk reference gets reused across many layers. The upshot is much lower memory traffic during decoding, which is the expensive part for long answers.
But they don't throw attention away entirely, right?
Right. They keep some cross-attention for expressivity because attention is good at precise retrieval. The trick is to swap out many of those layers for the cheap gate, not all of them. It's a balance between flexibility and efficiency.
Why should that balance work? What's the intuition?
The intuition is that the self-decoder has already compressed the prompt into a form that's informative enough for most of the generation steps. You don't need the full power of attention every single time. Most of the time, you just need to nudge the generation with the right slice of memory, and the gate is perfect for that.
Makes sense. How did they test whether this actually helps?
They trained small to mid-sized models and compared against standard transformer baselines and against setups that mix Yoko and hybrid layers without the new gate. They looked at long context retrieval tasks, like the synthetic phone book benchmark, and they checked reasoning tasks where the model has to produce long chain of thought. They also measured throughput in a popular serving engine to see the real-world speed during long generations.
And the results?
On long context retrieval, it holds up well, which is important because state-space models can sometimes lose track of very specific facts. The hybrid plus gate strikes a good balance. On reasoning, they report accuracy roughly on par with a strong small reasoning model while decoding much faster when the output is very long. Think big jump in tokens per second without giving up correctness.
So accuracy stays steady, speed goes up. That's the dream. Any idea how large the speed up is?
The paper talks about large gains for very long generations, on the order of a big multiple. The exact number depends on setup, but the story is clear. When the output stretches into the tens of thousands of tokens, cutting down those repeated memory reads pays off.
Let me push on the details. Is this just clever engineering, or do they show better scaling too?
They look at scaling behavior and suggest the new architecture learns efficiently as you scale compute. In other words, it's not just a serving trick. The loss curves indicate it's making good use of the training budget.
That's encouraging. But you know what I'm going to ask next. What are the caveats?
There are a few. First, some of the reasoning benchmarks are tiny. A set like AIME has only a handful of questions. A point or two up or down can just be noise. Second, retrieval suites like Phonebook are synthetic. They're useful, but organizing and producing coherent long-form text in the wild is a lot messier than pulling a phone number from a made-up directory.
Right, synthetic is a proxy, not the real world.
Exactly. Third, training recipes matter. If you mix in distillation or preference optimization, it can be hard to attribute gains purely to architecture. The authors try to control for that, but disentangling it perfectly is tricky. And finally, there's still at least one full attention path, so decoding cost goes down a lot, but it's not magically constant.
I like that last point. This is a big reduction, not a silver bullet.
That's the spirit. It's a pragmatic design that knocks out the most wasteful part of the process rather than chasing a theoretical ideal.
Let's circle back to the gate itself. If it's so small, why doesn't it hurt quality more?
Because it rides on the back of a strong summary. If Stage 1 builds a good compact memory, the gate's job is easy. It's like having a great executive briefing. You don't need the whole archive every time. You need a smart nudge drawn from the briefing. When that briefing is high quality, the nudge is enough most of the time.
And for the tricky moments, the model still has some full attention layers to lock onto specifics.
Exactly. You keep a few librarian-level lookups in the loop for precision.
If I'm running a product team, how should I think about deploying this kind of model?
2 angles. 1. If your users generate long answers, think legal summarization, code explanations, or detailed tutoring, you'll likely see throughput gains at the same quality bar. 2. System costs. Less memory traffic during decoding can mean better hardware utilization and lower serving costs for those long chats.
And what about research directions this opens up?
A few jump out. First, trimming the remaining attention path. You might replace it with sparse or dynamic attention so decoding becomes even lighter. Second, broader evaluation. We need more real long-form generation tests where the model must stay consistent and factual across many paragraphs, not just retrieve a single fact. Third, portability. It'd be great to verify the speed-ups across different serving stacks and hardware. And finally, training. How does this architecture behave with reinforcement learning or at much larger scales?
I like the portability point. Sometimes a fancy speed chart depends on one specific engine setup.
Totally. Replicating across stacks would make the case stronger.
One last clarification. We've mentioned state space models a few times. For listeners who haven't lived in that world, what's the intuition for why they're fast?
Good question. A state space model processes sequences like a conveyor belt. Instead of computing attention across all pairs of tokens, it updates a hidden state as it reads left to right. That gives you linear time and more predictable memory use. It's great for long spans. But because it's a streaming view, it can be less precise when you need to recall a specific token far back, which is why mixing with attention helps.
So the decoder hybrid decoder is like hiring two specialists. The first specialist skims quickly and writes an excellent brief. The second specialist does most of the talking using that brief, and only occasionally calls the archive to check a detail.
That's the perfect analogy.
All right, let's land this plane. What's the takeaway for our audience?
The takeaway is this. If you care about long chain of thought, the bottleneck is often memory traffic during decoding. This paper shows a practical way to reuse a strong summary of the prompt and replace many heavy lookups with a tiny gate. You keep the quality steady and make long generations significantly faster.
And the healthy skepticism?
Small test sets, synthetic retrieval, and training confounds mean we should treat the accuracy comparisons as parity rather than big wins. But the efficiency gains look real and meaningful.
I'm sold on the idea of fewer library trips. Faster answers, same confidence. That's a good trade.
Couldn't agree more. This has been AI Podcast. I'm Max.
And I'm Nina. Thanks for listening, and we'll see you next time.